Okay, hello everyone. Nice to meet you here. Today I'd like to tell you something about the physical composition of the GRB outflows. This is my outline. I will focus on the magnetic fiber mode. Let's begin with a general introduction of GRBs. Gamma ray bursts are short and intense gamma ray flashes from the space. This was the first gamma ray burst detected by Wheeler satellite in 1960s. Of course, at that moment, the time resolution was really bad. Now we have much better data. Yeah, this is the typical light curve of a long burst. One can say the prompt emission is highly variable. For all bursts, it's impossible to predict when and where it will take place. Statistically, GRBs distribute isotropically on the sky map. According to its duration, GRBs can be divided into two subgroups. One is a short burst with a typical duration about 0.2 seconds, and the other is a long burst with a typical duration about 20 seconds. When proposing such a classification, these authors didn't have any physical motivation, but now we know these two kinds of bursts have different physical origins. I will discuss this later. Usually, the GRB spectrum is long-form and can be fitted by a central block power function, the so-called band function. However, the spectra are not universal. One can say the power distribution indexes have a worldwide distribution. A typical low-energy spectrum can be approximated by mu to the 0, and in the high-energy band, proportional to mu to the minus 1.25. The fiber mode is the leading interpretation of gamma ray bursts. Why do people call them outflow or fireball? In the analysis of the prompt emission, people found variability time scale as short as sub-millisecond. That means the size of the GRB central energy is in order of 10 kilometers. If GRBs are at cosmological distances, the luminosity should be in order of 10 to the 52 erg per second. So you can estimate the initial temperature of the outflow. It should be in order of mega electron volt. So it's really hot. That's why people call it fireball. If the fireball is free of baryons, the spectrum should be somewhat inconsistent with the data. Such a problem could be solved if, in addition to the pairs and the photons, there is a small amount of baryon material. You know, the electrons associated with the protons increase the orbital depth of the fiber, particularly when the pairs are annihilated. As long as most of the thermal energy has been converted into the kinetic energy when the fiber is still optically safe for the photons, most of the thermal energy would have been converted into the kinetic energy of the baryon material. So the thermal radiation has been simply basically suppressed. The non-thermal photons we detected can be produced while some later energy dissipation of the accelerated baryon material. The fiber mode has quite a few really important predictions. First, GRBs are cosmological. Second, the outflows are ultra-relativistic, so there should be the low-frequency counterpart. On February 28, 1997, Sachs located on Bohr. The X-ray and optical follow-up observations detected the long-lasting afterglow emission, then confirming the sort of prediction directly. However, in this burst, people didn't get the redshift in real time. Such a goal was achieved in GRB 970508. Since then, the cosmological origin of GRBs has been firmly established. GRBs are cosmological events. The closest one to us was at a distance about 14 megapascal. So it's really difficult to measure something directly. But the expansion velocity of the blast wave may be an exception. For example, in this really bright nearby burst, GRB 030329, the radio afterglow was so bright that people could get the radio image and then the angular size as a function of time. With the distance informed along the redshift, people can get the apparent superluminal expansion velocity at a time about 3 weeks after the burst. The derived Bohr-Lorentz fact was still in order of 10. The early outflow, of course, should move much faster. So this provided us the first direct evidence of the ultra-relativistic movement of the GRB jet. Let's move on to the physical composition of the GRB outflows. For GRBs, there are two types of progenitors. In the cluster scenario, the progenitor is a massive star. After the collapse of the dense core, the acceleration onto the newborn black hole can launch ultra-relativistic outflow and then power GRB. In the model scenario, the progenitors are two compact objects. For example, double neutron stars, or one neutron star and one black hole. The cluster scenario may be mainly for the long bursts, particularly for those associated with a brighter type 1PC supernova. The model scenario may be mainly relevant to the short bursts because the acceleration disk formed in the module may be too small to survive longer than 1 second.
Well, it's important to mention that there is good evidence that your left scenario is indeed the dominant case for long GRBs, but for your binary merger origin for short GRBs, evidence is only circumstantial.
I agree. And some authors argued so in 1998, there was a paper in APJ. Some also argued the model can produce. Could produce long GRBs.
Should we skip some of the introduction? Because I mean, everybody here in this audience know all this, so what they are talking about. So should we just go to the point?
Yeah. This is the beginning. I'm sorry.
I ask you
because I never attended a workshop. So this is my first time to attend a workshop. I didn't know how to give a talk. So, okay, this is the main topic. In both the cluster and the module scenario, the fireball could be either baryonic or magnetic. Sometimes people call the baryonic fireball the hot fireball and the magnetic fireball the cold fireball. This is because for the later, the initial temperature is relatively lower. A baryonic fireball can be produced if by the annihilation of neutrino and antineutrinos. And a magnetic fireball can be generated if the central engine is a millisecond magnet, or alternatively, the central engine is still a black hole surrounded by the accretion disk, but the energy has been mainly extracted via some magnetic processes. I'm showing you the general picture of the baryonic fireball. Yeah, the so-called standard internal echo shock model for GRBs. In this model, the central engine is a black hole surrounded by an accretion disk. The accretion onto the black hole can launch really hard outflow. The outflow gets accelerated by the thermal pressure and then becomes transparent at a radius of about 10 to the 11 centimeters. As long as there is a small velocity dispersion of the material, the fast and slow but they collide with each other and produce strong shocks and give rise to front-port emission. The more the material keep moving and interact with the medium give rise to after emission. How about in the magnetic fiber mode? This is the mode proposed by Niels and Planck. The central engine is a millisecond magnet. The there is still hard component, but the photosphere is much smaller than that of the baryonic fiber because of the small amount of the baryon material. In this model, the front-port emission is poured at a very large radius, about 10 to the 16 centimeter, much larger than that in the internal shock mode.
Did they really require the central source to be a magnet, or can't it be just accretion onto a black hole?
This is just their picture. It could be a black hole surrounded by accretion disk. This, I don't think a magnet can use this.
This 10 to 16 centimeter is a genetic prediction, or are they just possible to produce emission at larger radius?
Which one? This?
Yeah.
I think they have some arguments for such a parameter.
I think their argument is that it's around the deceleration time, and that's when different parts of the flow come into puzzle contact, so that's where they expect most of the reconnection to take place.
Because of the really different physical composition, so people expect some signatures that can help us to distinguish between these two models. No matter the fiber is baryonic or magnetic, the initial acceleration may be very similar. So, for some component may be irrelevant. For reasonable parameters, in the baryonic fiber model, about 10% of the total energy will lose when thermal radiation. But in the magnetic fiber model, the thermal radiation may be very weak because most of the energy is in the form of magnetic field. What happens for the quote-unquote high energy gamma emission? In the baryonic fiber, or in both models, we interpret the soft gamma emission as a synchronous radiation of the electrons accelerated in the energy dissipation. In the baryonic fiber mode, usually the energy density of the generated magnetic field is much weaker than that of the electrons. So the synchrotron self-commute radiation should be very important. For reasonable parameters, some of these high energy photons will escape from the fiber and will appear as distinct GV axis. If correct, the detection prospect should be really pronounced. But in the magnetic fiber mode, because of the strong magnetic field involved in the emission region, the synchrotron circumference radiation is very likely to be weak, low GeV excess. Because of the huge numerosity and the really large Bohr factor, gamma ray bursts may be able to accelerate protons to ultra-high energies. For the standard intershock mode in the baryonic fiber, the acceleration process is relatively better understood. But for the magnetic fiber, we don't know whether the protons can be accelerated to such a high energy.
Without protons to begin with. It's not clear if you have a significant amount of protons if it's Poynting flux dominated.
Yeah, but I just mentioned whether the protons can be accelerated to such a high energy. I just mentioned the other two things. These really high energy protons, of course, will produce pions on the prompt gamma rays. The detection rate, of course, depends on the site of the prompt emission. In the standard intershock mode, this site is in order of 10 to the 14 centimeter. Singly based detection may be possible, but for the magnetic fiber mode, the PGV neutrinos may be too rare to be detected because of the huge radius of the prompt emission, as I have mentioned in Newton and Planck 4. This radius is in order of 10 to the 16 centimeter.
It's both this, and it's not clear you have a lot of energy in baryons to begin with, right?
Yeah, we don't care that just this factor kind of.
Even if it was at a smaller radius, but you didn't have much baryons, and you wouldn't have much neutrinos either.
That's another argument, but this argument also applies, I think. In the early phase of the interaction between the fiber and the medium, there are two shocks formed. One is for ultra-relative degree forward shock, the other is the sub-relative reverse shock. Usually the forward shock peaks in soft X-ray band, where the reverse shock peaks in infrared band. So one may expect that shortly after the gamma ray burst, there is a bright optic flash as detected in this host. Yeah, people interpreted this quickly decaying component as the reverse shock emission, and this generally declining component as the forward shock emission. For a baryonic fiber, usually people get a really bright optic flash. And such a flash may be detectable in more than a good fraction of bursts. But in the case of a magnetic fiber, the situation is a little bit more complicated. If the reverse shock is only weakly magnetized, the stronger the magnetization, the brighter the reverse shock optical emission. But if the magnetization is dynamically important, the reverse shock will be significantly suppressed, and the optical emission will be very weak. The polarimetry of prompt gamma rays may be an ideal proof of the nature of the outflows. In principle, in both models, or high linear polarization is possible, but the detection rates are very different. For the magnetic fiber, the detection or high linear polarization should be typical. This can be straightforwardly understood. You know, the charge outflows move moved ultra-relativistically. The photons we detected were from with a small cone with a half opening angle about 1 again. So as long as our line of sight was slightly off the symmetric axis of the magnetic field line, the directions of the magnetic field lines within the visible emitting region were more or less the same. So the polarization of these photons couldn't be effectively averaged. That's why usually people will detect a really high linear polarization. But in the baryonic fiber, or really high linear polarization is only obtainable when our line of sight is slightly outside of the edge of the jet. So the detection rate is not high.
Let me just say that even if your energy is dominated by the kinetic energy of the baryons, it doesn't mean that necessarily you have a perfectly random magnetic field. You could still have some sigma 0.1 field vectored from the source, and you can have it ordered in scales of at least 1 over gamma, which would also give you high polarization. So I do not agree that future measurement of tens of % of polarization would say you have to be Poynting flux dominated.
Yeah, but anyhow, it needs an audible magnetic field. If you
okay, but saying that necessarily fireball would lead to perfectly tangled magnetic field, we don't know that.
Yes, this I of course agree.
What's the point of this? Even if it's tangled, the polarization depends on the pressure, on the stress energy in terms of the field, not on the field itself. In other words, you can have you can have random field where the average field is 0, but BIBJ, average BIBJ is not 0, you get still high polarization. So what is the point?
Well, in this context, two fields people usually discuss on are either you have an ordered field with coherence lengths, angular coherence lengths of at least 1 over gamma, in which case you expect high polarization, or a magnetic field produced in shock, in which case one might expect it to be tangled in the plane of the shock, in which case if you see it as part of a patch of a uniform jet, you get no net polarization, but if you're viewing near the edge of the jet, you can get a few tens of % of polarization. That's what people usually discuss. You can have intermediate cases or anything in between. But it's not clear that...
All I'm saying is that the polarization tensor is, it depends on the isotropy of magnetic pressure, not the magnetic field itself. You agree?
What is that? Isotropy of
Magnetic pressure, not magnetic field itself.
boundary?
The local polarization depends on the local direction of the field.
No, it's not like it's the average of BIBJ, not the field itself. So the polarization is the average of BIBJ.
It's physical field line.
Yeah, but you can have a completely, average 0 field, but the second moment is not 0, and you still have polarization even though your average field.
It's not sensitive to the direction, if that's what you mean. If you have a magnetic field in one direction and the opposite direction, you would get the same polarization. So it doesn't cancel out, if that's what you mean. I agree, yes. But what we're talking about is not this symmetry, but whether you have perfect isotropy within a certain plane. So not in 3D, but in 2D. In which case, if you have a spherical geometry, you still average out to 0, since we don't resolve the source. So we effectively average over the whole source. And then you need to break the symmetry by introducing a jet geometry, etc.
Okay, the current data may help shed some light on the models. So this I will discuss in greater detail. Firstly, I'll discuss the optical flash modeling. The first optical flash was detected in GRB 0123. Though no new event had been detected in a long time, the reverse shock mode had still been widely accepted. In 2001, UNESCO and Kuma published their fate to the late afterglow. At that moment, I was a master's student in Nanjing University. I just tried to reproduce the early optical flash with their best fit parameters. Surprisingly, we found if the shock parameters were the same for the forward and the reverse shock regions, the resulting optical flash would be too weak to be consistent with the data. To remove such discrepancies, we had to assume with strong magnetic field in the reverse shock region, one can see the difference between the parameters epsilon b about 2.5 order of magnitude.
But you were not taking into account that magnetic field affects the dynamics. It was just the epsilon b that you were fitting there.
Of course we didn't, because at that moment.
Yeah.
But still, with parameter, I guess, still baryonic flow. So still, magnetic field doesn't affect hydrodynamics, I guess. With this
Epsilon b point. Well.
Yeah,
Okay.
just changed the parameters. We just changed the parameters here. Because at that moment, we didn't learn. So this might imply the magnetized reverse shock region. Okay. A more general approach had been presented by Copenhagen and Niels in 2003. According to their calculation, for an unmagnetized reverse shock, there should be double peaks in the optic band because the reverse shock was not strong enough to outshine the forward shock peak. However, for weakly magnetized reverse shock, the stronger the magnetization, the brighter the optic emission. So this peak could be hidden.
Well, why would it be at a later time? Why would the peak be at a later time?
This?
What's the question?
Why is the peak at a later time?
You mean the thinner case? Just not necessary to be.
So it's presentation.
Yeah, just
not
presentation.
output.
Look at the data, yeah, just one peak. So this also argued the weakly magnetized reverse shock region for GRB 123. Of course, the bright optical flashes are very real. So far, just about 10 units have been reported. Yeah, I guess in this post, the Liverpool telescope might have get some really interesting results. But at this moment, I don't know. Anyhow, almost all this modeling, people found a weakly magnetized reverse shock region. Particularly for the first post, 3 groups obtained almost the same result in 3 different ways. So the argument seems robust.
What are you claiming is a typical value of sigma people are getting from this modeling?
I think usually at most about 0.1. In the baryonic fiber mode, some component should be emerged in the spectrum, as identified in about 40 posts. For example, here one can see the band function failed to fit the data, but a thermal component plus a power component can reproduce the data nicely. I'd like to take such a phenomenon as the evidence for the baryonic fiber. But how about the non-detection in most other units? Particularly for recent post, GRB 080916C. This spectrum is a perfect band spectrum in the energy range 10 keV to 10 GeV. No any evidence for a thermal component. Some also, Zhang and Peel argued, yeah, the outflow should be point flux dominated. I think I agree with them, so I'd like to take this as a possible evidence of the point flux dominated fiber. In the optical flash modeling, people found a weakly magnetized reverse shock range. How about the absence of optical flash in most GRBs? As you can, yeah, these two figures are the results of two ground-based telescopes. If a reverse shock, if there is a reverse shock component, the temporal behavior should be like this, like this. One can say just a few such candidates. Then the optical flashes are indeed very rare. Among the real solutions put forward, I guess the magnetization may be natural. As shown in the numeric simulation by Mimic and even for neutral magnetization, the reverse shock emission has been significantly suppressed. Some possible evidence for the magnetic fiber mode emerged in 2002, but no one took them seriously until the claim of the detection of the high linear frequency GRB 021206. But now we know such a detection is highly questionable. Possible evidence have also been found in other forecasts. As learned in the X-ray polarimetry conference in Rome, the current best candidate might be GRB 041219A, but the error is still too large to convince the community. The optical polarimetry is much more reliable at this moment. People can also constrain the configuration of the magnetic field in the reverse shock region by measuring the polarization of the optical flashes. To achieve such a goal, people have to throw their telescopes to the burst in a time about 100 seconds after the burst. That's quite challenging. Actually, I joined one Italy group to measure the polarization of the optical flashes, but never got the chance to use on time. Anyhow, there was a successful observation not detection by the Liverpool telescope. They get a raw result, an upper limit about 8%. Yeah, this was the first. This was their measure time. However, in this post, we didn't have any evidence for a strong reverse shock emission, so the constraint on the models is very weak.
If you do detailed modeling, it's actually a single component. It's very consistent with standard. So
Yeah. I think that this optical emission should be mainly from the photoshop. So it's not strange to say there is low, the polarization degree is very low. Okay, the Montgomery Space Telescope was launched in last June. So far, about 6 bursts with significant GeV emission have been reported. Some bursts are really interesting. For example, in this burst, the high energy spectrum is a single power up to an energy about 10 GeV. Please note this burst is not nearby. It was at redshift about 4.4. So in the local frame of the Bohr, people didn't say they cut off up to an energy about 70 GeV. That is beyond my imagination. Anyhow, what interests me is the non-detection of a GeV spectral excess in almost all bursts. Frankly speaking, there are quite a few possible interpretations. For example, one can argue that the synchrotron self-content radiation of the standard interaction peaks at TeV energies. Such energetic photons couldn't escape from the fireball. So we didn't see the GeV excess. But one can also interpret the non-detection within the magnetic fiber model, because in this model the synchrotron self-content radiation is initially weak.
And of course that we don't see in the MEV peak the synchrotron component, but we see directly inverse Compton component, for example, and then there's no other component on top.
Yeah, but
I mean, in any
for
model.
For this post, for this post, the radius of the promotable emission has to be really large. Otherwise, this really high energy photons couldn't escape from the fiber. So if you argue this is the inverse Compton component, so the optic flux, there should be really bright optic emission.
Okay, it depends then on the specific model, I guess. But
Yeah.
In the Fermi, I missed the only talk that in the sources detected by Fermi, to what energy the spectrum extend?
Well, it depends on the event. In that particular event, the highest energy photon observed was 13 GeV. But it was at a redshift of 4.3, so if you go to the cosmological frame of the burst, it was around 70 GeV in its own frame.
And the other one? This is the highest.
The other ones, it's not reported yet, I can't say.
Okay, I just
So
want
what do you mean
to.
by non-detection of GeV?
Okay, I just want to summarize our current possible evidence for the negative fiber movement. Of course, the highly polarized gamma rays imply an ordered magnetic field in the emitting region, and the absence of a thermal emission component in most GRBs may be consistent with the Poynting flux dominated outflow mode. And the non-detection of GeV spectral excess is surely consistent with a strong magnetic field component in the emission region.
It's not obvious to me that if you have high sigma flow, you necessarily suppress
The thermal emission, you
the
mean,
SSC.
you mean to, I just argued Poynting flux dominated flux here, you mean the thermal emission can be
Not
suppressed?
thermal, the SSC, I don't see why you necessarily need to suppress the SSC in high sigma flow. You have a good argument for that.
Of course, I think I have. In the high sigma case. In the high sigma case, of course, actually, together with Sui, I mean, working on papers. But I will mention some of them was not later, okay? At least for me, these interpretations are self-consistent because before the prompt emission, the sigma could be high. But the energy dissipation will destroy most of the magnetic field. So when you try to see the magnetization in the Rorschach region, it's reasonably low. Okay, I think I will discuss something maybe more interesting. Yeah, the spectral problem of the magnetic fiber model. I also want to say the so-called low energy spectral crisis of the baryonic fiber model may have been solved by a model proposed by Delchev in 2001. Okay, why I say there should be a spectral problem? Yeah, the problem emission of a magnetic fiber has been calculated by Niels and his colleagues. Now I'm showing you their results in the case of radiomagnetic dissipation. In their mode, the electrons are accelerated by the magnetic reflection and are cooled by the thermal photons leaking from the outflow. The upper-scattered photons will be boosted to high energy and give rise to non-thermal tails. Look, in the low energy band, the model seems consistent with the data. But what happens in the high energy band? Yeah, this is the typical band spectrum. Yeah, this is what predicted in the model. I think there is a really big divergence.
So, excuse me, so the peak energy is determined by the synchrotron peak?
No, I think just by the thermal emission.
Sorry?
It's determined by the thermal emission.
So many?
The thermal, it's a photospheric.
Thermal.
Photosphere. Yeah, this is one of the photosphere. And I also wanted to say there might be the high energy cut-off problem. Look, in their spectrum, the powers cut off at an energy about 1 GeV. But in this post, people didn't say they cut off up to an energy about 70 GeV. Of course, in the local flame of the post.
So what is the enhancement in the low energy region? What is the what component in the low energy region?
Synchrotron.
This is the synchrotron relation of the electrons accelerated in the magnetic reflection. Okay. In this mode, the electrons are accelerated by the magnetic reflection. But in the mode by Newton and Blandov, the electrons are accelerated by the sudden magnetic energy dissipation at a radius about 10 to the 60 centimeters. They didn't calculate the spectrum. Let us do it right now. We just assume a single phasing of the magnetic energy has been dissipated. So the strength of the residual magnetic field can be estimated like this. Yeah, K is in order of 0.1. So about 0.9 fraction of the energy has been dissipated. If we interpolate this soft gamma radiation as a synchrotron radiation of the accelerated electrons, the random Lorentz factor has to be very large, in order of 10 to the 4. So the outflow has to be highly magnetized. Otherwise, the dissipated magnetic energy is not high enough to accelerate the electrons to such a typical Lorentz factor. We can also estimate the Cooling Lorentz factor. One can say the Cooling Lorentz factor for typical parameters. Gamma EC is much smaller than gamma EM, so the spectrum should be something like this. Unless you assume a very large gamma to get a gamma EC comparable to gamma EM, but I don't think such a large Bohr Lorentz factor is reasonable. Because in this case, you say gamma EM is very large, so that's why the SSC has been suppressed. I think this may answer your question.
It's not clear to me why it has to be this.
Yeah, because gamma EM is very large. So this photons with a typical energy about 600 keV will be in
If you have
either
sigma of 0.1 or sigma of 1,000 and
Oh, no,
for
no,
the
no,
same
no, no,
luminosity, the difference.
Klein-Schiene effect. That's the, it's a Klein-Schiene effect. It's a big.
Yeah.
Just a second, but the difference in the Lorentz factor of in the magnetic field is fairly small, and therefore in the required Lorentz factor of the electrons would be very small. Right. So if Poynting flask carries close to 100% of the energy, or only one half of the energy, it's a very small difference in the magnetic field. Right.
The SSA uses still in the Klein-Schiene region. Even for much smaller regions, for example, in order of 10 to the 14th millimeter, the same millimeter. Of course, the parameter, the numerator coefficients changing.
Probably the main difference is that you assume a much larger radius. So you have a smaller magnetic field because of that, so you need a larger domain.
I think this is reasonable. You can say, even for back Lorentz factor about 300, I think this is really reasonable. You will get. It has to be very large. It has to be very large. I think 10 to the 14 should be a typical parameter. Should be a typical weightage.
Okay, so to understand the Lutikoff and Blandford picture, there were also jets, essentially rapid motions within the jet itself. You don't assume such motions in your picture here.
I just here I didn't assume anything. Just assume the soft gamma radiation is attributed to the synchrotron radiation of the accelerated electrons. This is what I assumed. I didn't assume any other. So okay, I know a lot of people here have interest in the low energy spectrum of GRBs because in this is UFU. Okay, in the standard model it should be like this. But what we overload? It's much clearer. And there is a special session on this. Actually, for me, I think this problem has been solved by Dennis Schiff in 2001. But I don't know why this model has been ignored for such a long time. The idea is not really complicated. Yeah, they just assume, yeah, this is the typical Lorentz factor of the electrons, corresponding to the nu m, to the peak of the nu f nu spectrum. And but such electrons, the electrons in this energy range suffer simply based on the inverse complement emission, but with the Klein-Schiene region. So for these electrons, the theta photons are in this energy range. But for the electrons have a much smaller Lorentz factor, this theta photons could be in this energy range. So a self-consistent solution will give really interesting result. This just a copy from the paper. They found the energy distribution of the electrons is not the regular gamma E, regular But I found that this is not correct in this this region, it should be proportional to gamma e to the minus 1. And the spectrum, of course, is not the F nu proportional to the minus 1 half. It is proportional to the 0. And recently, Sylvia and I found for typical GRB levels, this model works perfectly. I just want to mention what are the typical parameters we use. I think the wind rhythm and the E peak I think we didn't assume anything additional.
How about sigma? You don't need the assumption of the sigma.
Sigma? No. This is better in the hard fiber. The back need fiber. It is not in the vacuum fiber. So I think in the standard mode, the so-called low energy spectral crisis has been solved. However, in this mode, the epsilon E has to be much larger than epsilon B. Otherwise, the universe company will be too weak to modify the energy distribution of the electrons and then the spectrum. So this is my comment on the magnetic fiber mode. We don't know, but there could be some tests. On this interpretation. For example, because this interpretation only works for GRBs, not for X-ray flashes. Why? Because X-ray flashes have a really low E peak. But this model depends on this parameter. Relative sensitivity. However, for X-ray flashes, the low energy spectral index cannot be weighted reliably. So, finally, I'd like to share you my opinion on the physical composition of GRB overflows. I don't think one mode can reproduce all the data. There should be a distribution. Some of fibers are baryonic, some of them are magnetic, some are between. This is what I believe.
Just to comment that sigma, of course, can depend on distance. I mean, if you accelerate the flow, your sigma drops. So sigma that you get, for example, from the reverse.
That's exactly what you said, I think.
Okay.
Yes, the sigma should be R dependent, the radius dependent.
So which sigma are you referring in the last?
Not only radius dependent. If you have local reconnection events, it could be in that particular
So in this block,
place. You might have lower sigma than around it. So even in the same radius, it can vary within the flow.
As I understand, that's it? Yeah? Yes, okay. Thank you.
Thanks.